So I started out as a microbiologist coming out of undergrad. I went to Harvard Medical School and worked in medical microbiology there, and I was kind of deciding, do I want to go in environmental, follow my interest in that area, or into medical technology. Decided environmental. I went to a graduate school where I got my master's, and a man named Barry Commoner. Anybody know about The Closing Circle, The Poverty of Power? He was a key author way back when I was in college, which was a long time ago. And he influenced my thinking a lot. And then I went in environmental fate, in effect, worked as a chemical hazard information profiles with EPA, spent some time where I directed an environmental fate and effect laboratory. Two key things I did there. One is I directed a laboratory where we tested compounds. For example, helped consumer product industry develop more biodegradable surfactants. And also I spent a lot of time on hazardous waste sites, cleaning up sites where the military and some industrial ones as well. So I spent a lot of time walking around on the Rocky Mountain Arsenal. I was dressed a little differently then, Tyvek suits, very uncomfortable way to be dressed. And then I spent about 20 years in the pharmaceutical industry working for Pfizer. So that's a little bit about my background, how I got to be where I am now. I'm working on my own as a consulting now, and I've been doing work with the ACS. So we're going to talk about Green Chemistry Principle 1, which is all about waste. And it's an overarching principle, and so this talk will be much the same way. So here's what we're going to cycle through. We're going to talk a little bit about the problem of waste and how it's been thought out in terms of the environmental agencies, EPA, for example. And then we're going to end the discussion on some tools that you can apply to pursue green chemistry initiatives to help you decide what are the most important issues to follow and to monitor your progress. All right, so green chemistry principle number 1, better to prevent waste than to treat or clean up waste after it's formed. So the scope here is across not just the manufacturing processes, but also the products that result from there. Priorities, avoiding inefficiencies, and the production of unwanted materials. These are the learning objectives. So let's talk with the problem of chemical waste. What is it, and should we focus on it? First image that pops to most people's minds when they think about chemical waste is the type of thing you find in hazardous waste sites. But it's really much more than that. It is emissions to air, not just from factories, but from people's houses. Domestic wastewater, wastewater that comes out of people's houses, all the materials that are used, for example, in the bathroom, go down the sink, musk, detergents, all the other materials that are used, enter domestic wastewater. So there's really much more than just an industrial contribution to wastewater. So while industry gets a lot of blame, and rightly so in many cases, there are many other contributors, and we are all among them. When we take a look at what waste is, there's lots of ways you can define it. I've got a few thoughts up in that first bullet, but I want to spend some time on the second bullet and talk about what waste is in other contexts as well. So it's a symptom of inefficiency. It's a safety risk, both to humans and the environment. It's a non-sustainable situation, as Dave has already well characterized. And to me, it's really a symptom of an innovation deficit in human creativity and intellectual rigor. And there's a lot of it out there. This is a UK waste profile across all the sectors. You see 330 million tons. This is, in 2003, the US municipal solid waste, 236 million tons. And now I want to spend a little bit of time on the implications of waste. And I'm going to do that in the context of this analysis that Richard Smalley put together with some of his colleagues, where they identified a number of problems for humanity. And these were the top 4 problems. And I'm going to show how green chemistry and waste link into all of those. And within the context of those problems, it's important to think about a couple things. David's already talked about the population. That's certainly one of them. And within that, all people really have a right to the quality of life that many of us enjoy today. And also, as developing nations develop further, there's more and more preference to have the kinds of things that we have available to us today, which puts much more pressure on the systems that are out there. So waste is really an integral component of all of these problems, and I'm going to show a little bit on each of these. And in the bottom right corner, I talked it's more than just industry. It's all of us that really contribute to the waste situation that's out there. So let's talk energy. And this is a slide that says, how is this going to work out? We're looking at China. If they have the number of cars that we do today, and the world currently has 860 million cars, well, in 2030, how are we going to deal with 1.1 billion cars when those cars would require more oil than we're current global production today? You just think about that and say, how's that going to work out? Well, it's not. So we have to do something different. So it's more than just continuing what we're currently doing today. Something else needs to happen. Water. Again, you take a look at the current situation. There's 20% of the world's population that don't have safe drinking water. Double that number that don't have sanitary conditions. Can we afford to continue to pollute water in a way that makes it unusable to humanity? Well, we really can't do that. We have to do a better job. Reducing waste is a good start. Contaminants in the food chain. This cartoon points out mercury, but there are many others. All you have to do is pick up a newspaper. Over the course of a week, you're bound to see at least one instance where there's something about pollution, contaminants in the food chain. Now what I want to talk about is money and the wasteful use of money. And I'm going to present this slide in a way that tries to accomplish two things. I want to talk about the value proposition of green chemistry for industry, why it's important to industry. And in doing that, I also am going to try and show how money is wasted without green chemistry implementation and by continuing to produce waste. So when you're in industry, waste is not inexpensive. There's 3 different ways that it hits the bottom line. So you buy starting materials or resources that end up just being disposed of as waste. So it's a wasteful purchase right at the start. You utilize the materials, and utilizing materials in an industrial setting is much different than, we have a beaker or a flask at the end of the lab bench that we pour something in. You're talking about dedicated facilities for storage materials. You're talking about handling materials, and then you're ultimately talking about disposing them as well. And this shows the magnitude of what can be accomplished with green chemistry. So you look at these 3 major bullets and you see the contribution from just 16 years of Presidential Green Chemistry Challenge workers. So we're talking about 16, 20 different chemical syntheses and the contributions those made to decreasing environmental loading of contaminants. And you think about, now what could happen if the 80 to 90 to 100,000 compounds had these kind of green chemistry applications to them. Pollution prevention is more than just dealing with waste, it's really reducing waste. So here's a conceptualization, a waste minimization hierarchy that shows preferred environmental options. And you can see at the top is really reducing the formation of waste right in the beginning. And that's what a lot of today is all about, is reducing the formation of waste. This is another slide, much the same concept. Here you see the increase in cost, the axis on the left, and then also the decrease in hazard and risk, the axis on the right. But source reduction certainly takes more time to reduce the waste, but it certainly makes a big contribution compared to simply disposing. Now what I want to talk about is how can chemists understand where the most impactful places are to conduct green chemistry, and how can you measure your progress? Measuring progress is really critical. You have to have good metrics to be able to understand whether you're making progress or not. I'm going to talk about 2 factors, E factor, environmental factor, and process mass intensity as decision-making tools. So here's a chemical process representation, and you have materials coming out on the right side, you have product, you have waste. E factor is simply the kilograms of waste, kilograms of product. You take a look at E factor results. These were published in 1992 by Sheldon, and you see the pharmaceutical industry jumps out right at the top. We're 25 to 100 for an E factor. You might say, well, there's all that purity that you need to achieve with pharmaceuticals and all that processing complex molecules, and say, oh, okay, we'll give them a pass on that. Well, the pharmaceutical industry looked at these numbers, and after a brief period of saying, no, that can't be us, you know, and then they say, well, what can we do? And actually, example with a Pfizer project, Lyrica, you've probably seen on TV, paper ads. They were able to take the E factor from about 88 down to 12, and among the savings were roughly the amount of CO2 from a year's worth of about 70,000 cars off the road. PMI, here you're involving the left side, so you're taking raw materials and product, quantity of raw materials divided by the quantity of API produced. Active pharmaceutical ingredient here for pharmaceuticals, but you know, whatever the product may be. The Pharmaceutical Roundtable, part of the GCI, developed a PMI calculator tool. This is all publicly available. You can just plug in your numbers and get a PMI calculated. And it's calculated not just overall, but you can do it for solvents, waste, reagents. And this is a great illustration of a cross-section of 46 processes. And you look at this and you say, now where would I pick a compound to start working on green chemistry initiatives? Well, you're over on the left side, you know, because you have all that material. And you can see the breakdown in terms of solvents or other materials. So this gives you the initial information to start to take a deeper dive into that particular process and say, how can we do better? The contributions of solvents was really noted here. So 58%, it provides this insight about reducing solvents, reducing the hazard of solvents. And from that, this Pharmaceutical Roundtable developed this solvent selection guide. And you see as you sweep across some of these, you remember that David pointed out, it's not a clear slam dunk in most cases. There are trade-offs involved. So you pick, you know, one compound, you may get more of an environmental issue. You pick another, you might have a safety issue. You can factor that into how is this material going to be used? Where is it easiest for me to deal with a problem? This solvent selection guide has also been rolled out, publicly available. And summarizing E factor and PMI. So they're simple, powerful tools that reflect material use. They're practical, they're easy to understand, and especially easy to communicate. Communication within industry is really critical. Incidentally, I want to just sweep back to that example of Pfizer. You might say, well, how did that happen? You know, what started that? Was there some edict from management on high that said, you know, thou shalt find ways to reduce waste in this process? No, it wasn't like that at all. The way that happened is you have innovation and creativity by somebody on the bench looking at this process. This happened to be a person who was interested in bioprocessing, and they thought about a way that they could improve that synthetic process by a biocatalytic process, and they were able to develop that. They were able to get management approval, and it went on. So speaking to that point, you know, you, when you're out there working, you know, don't necessarily wait for things to come down from up top and before you initiate something. There is a lot of room for innovation and initiative. And if you're working somewhere that doesn't enable that, you know, find someplace else to work. You know, because that's really the way a lot of these things happen. These factors, E factor and PMI, they open the opportunity to examine the next level of detail, and that's really critical to be able to do. It targets an area, a process that could use some attention, and then you start to drill a little deeper on that. Another thing, reducing PM and E factor, as you'd expect, it always makes the process greener, but it always makes the process less costly, which catches a lot of people's attention in industry. So the key learning points I want to wrap up with are the problems of waste include inefficient use of resources, but it goes much beyond that. It's also capital. It's a broad sweeping amount of inefficiencies. It's important to society and the environment to reduce these risks. Most developed nations already have recycling, energy efficiency program. They're all good. They need to be more in place. And at the process level, as you would imagine, based on things I've already said, process flow sheets are really important to highlight the sources of waste. And A final thought, and we'll drill into this theme a little bit more in some other talks, is most chemical products end up in the environment, and they really should be designed for recycling or for degradation. And degradation we'll talk about as Green Chemistry Principle 10. So with that, any questions? I'm sorry, I missed the question.
I was surprised to see that oil refining has such a low E factor on your terms there.
Mm-hmm.
Is that just because that formula is derived from some of the products that come out of that process as opposed to
I'm sorry, I'm still.
oil refining? Yeah, what does it have such a low E factor?
Why does what have?
Oil refining, yeah.
I'm sorry, what? Oh, oil refining. Oh, it's a much simpler process in terms of what comes out of the ground is closer to what you end up with. And there's a lot of very extensive technology development that has occurred over the years. I'm sorry, I'm deaf in one ear, so I was having a little trouble hearing you. Any other questions?
Do you think that if some of these processes you described had also had the decades, would the E factors also go down? Because oil refining has been like...
It's been around for a long time. Talking about pharmaceuticals, so innovative pharmaceuticals, they have a certain patent life, and during that period of patent life, there's more ability, more emphasis on, especially early in the process, where you have a defined period of time to recoup the money you invest. So the patent protection piece with pharmaceuticals has a big impact on when the work is done and how it's done. So early on, just after a compound has been approved, and there's 10-ish, 12-ish years for a company to recoup its investment, it'll be more likely that the green chemistry is done early on. If it's right at the end of a patent protection period and it's just about ready to go generic, there isn't as much incentive to work on it then. Any other questions? Yeah. So the question is, let me know, why wouldn't a company just be doing this all the time anyways? Yeah. Well, there's a couple things involved there. I think waste in general isn't as an appealing a topic for example, for upper management to think about. You know, waste, we'll have somebody else who'll worry about that. I will say that within the pharmaceutical industry, the way the process evolved is, so Sheldon published that paper, and pharmaceuticals are right up there. Well, that's not the way the pharmaceutical industry wanted to be recognized out there in the general community. So the first reaction was along the lines of, and this isn't universally true, but it's pretty close, was, oh, no, you know, our compounds have to be so pure, you know, there's nothing else we can do, you know, it's inevitable that we have to produce all this waste. And then some people started to look at it and to think a little bit more deeply about it. Well, you know, can we improve that? And then they started to say, well, yeah, you know, we can. And a lot of this is linked to technology advances. You know, there's new technology. It's not like all chemistry is known. People find innovative ways to do something different. A new chemical transformation, the biocatalysis process, something that enables an innovative look at how do we make this material and can we make it better. And so once those things started to happen, once companies recognized that some other company was saving this kind of money, was able to do these kind of things, then, you know, the fever kind of catches hold and, you know, it sweeps across the industry.
So I'm going to have to cut you off.
Okay.
It's like I said, we're going to be pretty ruthless with keeping time, otherwise we'll get way off schedule. You'll find in your packets an exercise number 2 on mass intensity and E factor. And it's front and back page, and there's some questions. So this is going to ask you to do the problem on the front, look at mass intensity and E-factor, and then answer the questions on the back. And again, you'll have about 20 minutes, or 15 minutes, 15 minutes to do this.